Good morning. We're coming to you from Myanmar, so we'd like to acknowledge the traditional owners of the traditional custodians of the land where we work and study. I'm actually on Nyanjan country, so the languages of the Turrbal and Yagara. Today's lecture is on natural language processing. And for this lecture, we'd particularly like to thank Dan Vanesh, who's been working with us to put together the structure and to try and make it relevant to the goals of the Voyages course. And I'm going to hand over to Ben Foley to start the lecture. Ben.
Thanks, Janet. Natural language processing. So what is it? We're going to cover a lot of different approaches to natural language processing. And by the end of the lecture, we'll hopefully understand what language processing is and even what natural language is. We'll see some applications of natural language processing in various language technologies, and we'll hopefully have some understanding of some data requirements. So this word cloud on the slide names in a rather scrambled kind of way some natural language processing techniques and applications. We'll see that NLP can be used from very simple language tech like keyboards, digital keyboards and spelling corrections on your mobile through to sophisticated conversational AI in chatbots. This came up in the first lecture, this question about what is natural language and the difference between natural languages and programming languages. So in NLP and language tech development, natural language is a term used to refer to human languages, whereas programming languages are more often referred to as formal languages. So this distinction between human languages and formal languages, or natural languages and formal languages, we'll see in a moment some of the characteristics of these different languages. Natural language processing are techniques to convert human language into formal languages that are more easily readable by computers. So here's a comparison table of natural languages and formal languages. The differences listed at the top. So think about human languages that you know compared with programming languages that you know. Natural languages, human languages tend to have evolved over time, over significant periods of time. You could say that programming languages also evolve over time, but they tend to be designed more so than haphazard evolutions. In the evolution of a programming language, you'll often get some additions to the language to enable further functionality, but there tends to be a very consistent schema or set of rules by which those additions to the language are allowed. Natural languages, human languages tend to be very ambiguous. You can say something in language which can be interpreted in many different ways. This tends to be very poor effect in a programming language, so formal languages are much more literal. If you give an instruction in a programming language, that's generally anticipated what the output can be. You can test for the output of an instruction and you can be guaranteed that the results are going to be consistent. Natural languages, because of this ambiguity, they tend to have a lot of redundancy in them. So you can give the same instruction or you can say the same thing in many different ways. The classic examples of French having 40 different ways of saying love, Inuit languages having dozens of ways of describing snow. So there's a lot of redundancy in human languages, less so in formal languages. And natural languages, we can break the rules all the time. So if there are particular grammatical rules or syntactical rules about the structure or the use of words in the language, we can break them and still communicate. If you've seen the communication of teenagers in social media channels recently, and you can see that, or Twitter communications over the last decade, the rules of English are broken all the time, and people still are managing to communicate with other humans. So formal languages, if you break the rules, you tend to not be able to compile, a program won't run. The rules are very strict, and the consequences of breaking the rules being that there's a communication breakdown. Human languages and natural languages have these words in them that are conceptual. So words like love, words like hope. The meaning of words is very context dependent and based on the experiences of the people who are using those words. So in formal languages, words are very well defined, and you can look up the meaning of the words in documentation, and hopefully if the language has been well documented, and the intent of the word is very clear. And yet natural languages and formal languages have things in common. So they are all made of tokens. We'll see in a moment in more detail what tokens can refer to. Think of words. They have syntax and grammars, so structures around the organizations of those words. And conforming to those syntax and grammar rules is what can help to define one language distinct from another. So in this course, we're looking at natural language processing, which is a process of converting natural languages, the data of natural languages into formats that formal languages can work with. Here are some processing types. So some different types of NLP. In our NLP broadly can be broken into three parent groups: natural language processing, natural language understanding, and language generation. So in the module today, we'll look at natural language processing, which tends to be techniques around formatting, data preparation, and extracting information out of natural language. We'll look at some natural language understanding processes. And so these, as the name suggests, this is where we go a little bit beyond simply reformatting texts into trying to understand the meaning behind them. Language generation we'll leave to a later module, and we'll go in more detail into language models and language generation, where we'll look at data to text summarization and Q&A, question and answering techniques that'll come up later in the course. Different people might list these subtopics in different sections. So some people might put syntactic parsing in the NLU group. This is just the way that we've arranged it in this module. Natural language processing. Two turtles by the lake. Janet, I think, has some significance for these turtles that maybe we can talk about in the chat. These turtles live at the University of Queensland. Some say they are mythical beasts. Tokenization, so natural languages and formal languages both made of tokens. And we can think of tokenization as a process of splitting some input into tokens, and a token could be a sentence level slice of the input, or it could be a word level slice of the input. You can tokenize into smaller chunks or smaller segments, down to morpheme or phoneme or character level tokenization. So a token is an element of a text. In NLP, we're tending to use text language data. NLP very broadly also covers other aspects of language technology, such as speech recognition and text-to-speech and machine translation. We'll also keep detailed descriptions of those for future modules in the course. As NLP has traditionally been a field working with text. We'll start to see in the next few years that as techniques for working with speech and video data become more available, that NLP techniques will be used more directly on sound signals rather than currently converting into text and then doing NLP on the text. So it's a bit of there we go, a good, nice example of the ambiguity of human language, that I can use the term natural language processing to talk about a very broad concept, as well as using the same term to talk about a specific group of processing tasks within it. So through this module, we'll now use NLP to talk about these tasks that are operating on text. Come back into the course in a few years and we might have some more applications of these tokenization or these other processing stages directly on speech and video signals. So in this example, the input sentence, 2 times a day I walk to the shop. The shop owner says hello both times. This is an utterance, some very simple English language, 2 sentences. We can tokenize that as 2 individual sentences shown in those 2 big grey boxes, or we can tokenize that down into these individual word and punctuation tokens. Now, that could be done by hand with some simple Python script to iterate over that. And one approach might be to split that up by spaces, in which case we'd get we could first slice that input text by full stops, maybe some regular expression matching to identify those individual sentences. That would be fairly straightforward. And we could write a simple Python script to iterate over those sentences and separate or split the words up into tokens based on the spaces between words. In this simple English, that would also be fairly trivial. However, if we were working on a more, say, a recording of some conversational speech, or maybe some very technical domain-specific language from maybe a medical observation, then the regular expression rules or the slicing rules that we'd have to write might become so complex that they become kind of impossible to manage. So fortunately, to perform this tokenization, we can use existing tools such as the Natural Language Toolkit, Nltk. And you'll see through, particularly in the tutorial, we'll use Nltk to do a lot of the processing. So Nltk is a very mature Python package, and it has existing methods for doing lots of these NLP tasks that we'll see today. So to create either of these examples, we can just use Nltk and import the tokenization package and use a sentence tokenizer or a word tokenizer to split that input up. Stemming or lemmatizing is a NLP process where we group similar forms of words around a common base word or the dictionary form of a word. So English, or many languages, modify words to express different attributes. So we can express tense or say past, present, or future tense of a word by sticking bits onto those, affixing or prefixing or suffixing characters onto a base word. to change the meaning of the word. So we can see this example voyage or voyages, voyaging. The base word is voyage, and we can modify the meaning of that word. Say that make a present tense voyaging by appending the ing morpheme onto the base word. The words can be modified with punctuation, and words can also there can be similar forms of words that we might want to group to a common base word, as we can see in the second example. So these two processes, stemming and lemmatizing. Stemming is very crude. Tends to be done just by having a list of suffixes or prefixes, so es, ing, and using that list to chop off bits from input words and leaving a base word, and then counting the number of similar base words. And it's very crude. That can work in some languages, doesn't work particularly well in other languages, and misses the second form there, the grouping of like words into a common base, unless you have a large dictionary or prepared data set of similar words that you can combine. So you could do that with lots of rules, but it could become, again, very cumbersome. The lemmatizing is a more sophisticated approach. It can group words to, you can group words by using part of speech tags. We'll see in more detail what a part of speech tag is, but for now, think of a part of speech tag as being something like is this word a noun or a verb or an adverb? And then lemmatizing can use the context of a word to also identify whether it's grouped, and this helps in languages where you can use the same word to mean different things. So that example sentence from the previous slide, 2 times a day I walk to the shop, and the shop owner says hello both times. So when we lemmatize that, we have lost the times has conformed to time. So 2 times a day I walk to the shop. We'd lose the punctuation. Punctuation's not important in English, but it might be in other languages where it could denote tone, different tonal meaning. The shop owner says hello both times. So again, we've collapsed the plurals into singular forms. There's a link. I don't know if I can get it out of. Nope. So if you want to try stemming yourself, there's a link on the slide. I'll just type that into the chat. textprocessing.com/demo/stem. Have a play with that while we're going through the slides. It's kind of fun to see how they work. So if we're not using rules, we can use existing libraries that can perform these techniques, and it then depends on what the libraries have been trained on as to the results. Some of these techniques or the demos can give you options to play with different libraries as well. So here we go, parts of speech. So parts of speech are labels that identify the functions of words or the grammar, the performance of words in the grammar of the language. The list on the right-hand side of the slide are some of the more common part of speech tags that we can access using Nltk. So when we do Nltk automatic part of speech tagging, then these are the tags that we will see, and the meaning of them is listed there, and some examples. So an example noun might be the word Africa. So if we had a sentence, Africa, if we part of speech tagging the word noun, sorry, the part of speech tag the word Africa, we'll have the tag noun. So in our example, Dan, look, there's a turtle in the lake. The parts of speech for this sentence are glossed underneath it. NNP is a proper noun. Punctuation is marked with a full stop in Nltk. Look, another noun, singular noun. There is tagged as existential. Is, present tense verb. A, determiner. Turtle, noun. In, the preposition. The, another determiner. And lake, another singular noun. And finish with a punctuation mark. So we don't need to know what existential means in this module. It's enough to know that when we perform part of speech tagging, we get these labels that we can work with. Now, some natural languages have very formal or have particular rules around the way that their sentences are made up. So subject, object, verb, and within those, the subject might tend to be, say, determiner noun. So if you happen to know the grammar of a human language, it can help in the forming of sentences and the reading of these. But you'll see that some of the technologies that we're looking at today will use these parts of speech tags as a way to get more information about the way that they process the text. And so it's important for us to at least recognize that these parts of speech have been tagged, and then we can look up using the Nltk list, for example, or a big grammar list to see what the codes mean. Chunking is this process of grouping tags or grouping parts of the input, parts of the sentence. So we can see in this deconstruction graph that the sentence can be broken down into individual parts of speech. So we have, again, 2 times a day I walk to the shop. The parts of speech have been labeled on each of the sentence tokens. And then within that sentence, we can group or chunk individual tokens into phrases or other chunks. So in this sentence, we have 2 noun phrases, which one of them circled there, the other one is the shop. And this process really helps us to break sentences down to find out where meaningful words are and what other words are associated or attached to the meaningful words. This can be handy for technologies such as machine translation, where we might translate an entire noun phrase rather than trying to translate individual words. And we'll see it being used later on in entity detection, which is where we identify the names or the locations in some text. So again, there's a link on the slides if you want to try some chunking by yourself as we work through it. This is an example that I put in just before. I'll see if I can make that a bit larger so we can see. So Spacey.io has an interactive sort of sandpit area where you can play with some code to do some chunking. So it's a Python, little Python script. We can import the Spacey package. We'll load this English tokenizer part of speech tagger and NER, named entity recognition, module, and then we'll use that to process some text. So the text that I put in there is this sentence from the introduction to the course, Voyages in Language Technologies, general introduction to the world's languages, including an overview of essential language and linguistics terminologies. So when we perform the chunking on this input text, we can see down the bottom there that we are given a group of a bunch of noun phrases. So the noun phrases are listed. A general introduction is a noun phrase. The world's languages is another noun phrase. An overview, and this much longer one, essential language and linguistics terminologies. So this last one is quite an interesting deduction, that it hasn't just given us linguistics terminology as one noun phrase and essential language as another noun phrase. It's identified that that is an entire kind of unit of meaning in there, and so that's been identified by the parser in this. And we also get our verbs out of, shows us then any verbs if the token has been tagged as a part of speech verb. So that's a nice little piece of code to play with as well. Try putting in some other text and see what your results are. Maybe you can give us in the chat a couple of noun phrases from some random text that you put in. So related to these morphological analysis, this is, in a way, it's similar to the tokenization. Similar to the way that we group the meaningful parts of words or meaningful words. With morphological analysis, we are looking further into this by seeing how the words are broken up into individual morphemes. And so this can help us in these other processes where we can break down the words into morphemes and then perform those other processes like grouping on them. So again, we'll use the word example, voyages. So we have the root of the word is voyage. So that's the primary morpheme of that word. We have the S is an affix onto that word. So we can change words by affixes, prefixes or suffixes or infixes are different types of affixes. So prefix is something that's been added to the beginning of a word. Suffix has been added to the end, and infix is a change to a word, typically a vowel in the middle of a word, to alter the meaning of it. So run can be changed by the affix of ran. Another form of morphological adaptation is non-concatenative. So we can change foot to feet or tooth to teeth by changing these in between, these inner parts of the word. Now, some languages are extremely complex, have extremely complex morphemes. I just want to show this example from William Lane's work building a morphological parser for Kunwinku language. And this word shown on the slide here, it means he took them down under the water. Ben Yi Bin. The top row here is the word that's been transcribed with dashes separating the different morphemes. This is a gloss. And then we have a translation. The table at the top is a breakdown of how the morpheme composition works in this language. So the 0 point here over towards the right is the stem of the verb stem of the word. And then we can see that the language has this quite regular sequence by which prefixes and suffixes can be added to develop the word. So the word can end up with 12, up to 12 morphemes attached to it and some suffixes. So William was developing an analyzer which could pass an input text and break it down into these glosses, or also take these glosses as an input and generate the word form from that. So it's just interesting here to see that individual words can be incredibly complex in some languages, and yet we can try and find form in those. Now, the reasons for breaking down these words into the morphemes might be that if we were training a speech recognition system on a morphologically complex language, then we might have fewer instances of individual words in the training data, because each word being complex might only appear a very small number of times, whereas the individual morphemes themselves might appear more often. So if we break the words down into separate morphemes, then we might see more instances of those morphemes in the input in the training data, and our recognition system might then be higher quality. So breaking them down into morphemes can be better for training other systems. Now, doing this by hand, again, would be painful, and trying to write individual rules like regular expression rules for most languages would also be nigh impossible. So William was looking at the approach of using finite state machines to do that, and we'll talk about finite state machines in detail in a future module, and also comparing that with neural network approaches of learning from input data. The link at the top of this slide, Morphessa, is a tool for breaking input texts down into the morphemes. So again, that's something we can play with. I wonder, does anybody have any questions at this point? Feel free to drop questions into the chat as we go along. Named entity recognition is a process of, again, we're extracting information out of the text and labeling it. So this technique extracts labels such as, or extracts information from the text and labels them with these categories like person, location, organization. So from an input text, we can pass the text, then extract all of the labels, or extract all of the tokens that are people's names. Now, this helps with sorting data. We'll see that it is a process that's very useful in these techniques like slot filling, which we'll look at soon, where we're taking some input data, we're trying to find where the significant pieces of tokens of meaning in that input data are. So it can also be used to sort and organize unstructured data, so data that doesn't have an internal structure or kind of rigorous storage structure, into a structured data format. So something that might be more easily represented in something like a relational database. So we could deconstruct this example sentence, Dan saw Alfie the turtle in the lake, and store that information in a table that's had, say, listed the people. So person 1, Dan, person 2, Alfie. Now this NER system hasn't learnt that turtles aren't people, but it's just a label. So this is an entity that's been labeled as a person. So could be confusing if Alfie was actually a human, but we could potentially train NER system to label things with person, label things with animal. So the categories are dependent on the way that the system has been trained. Now, putting some of these things together, those up to now we've been looking at kind of discrete tasks of tokenizing and chunking, part of speech tagging. So in themselves, they are maybe interesting kind of programming activities. I've been to conferences where people like to announce that they've developed a new part of speech tagger for a particular language. So that's all very important as parts of developing technologies that can get to be useful for people in day-to-day communications. So this process dependency or syntactic parsing is slightly next level, where it's combining a few other tokenization and part of speech tagging techniques into then looking at the relationships between words in a sentence. So these dependency trees can become extremely complex. This is a fairly simple one, just using the Voyages in Language Technologies phrase. We can, again, there's a link on the page there that you can try this with your own input text. The arrows in the diagram represent the relationships, and that we can recognize the part of speech tags tell us a little bit about how that phrase is made up. So we have some nouns in there, and so plural nouns, NNS, in, NN is the noun, and then the labels that are on the arrow line are labels about the modification method. So nmod is a noun phrase that functions, or a noun that functions as a modifier. So this is modifying the technologies. There's case marking, so there's shows a dependency. So the case marking in technologies, and the compound, the noun compound modifier, is a noun that serves to modify this head. So the technologies here is the head word, language is modifying the technologies. So it's adding more information to it. Let's have a look at another example of this. So the lemmatizing example from before, lemmatizing Dan saw the turtles, gives us this lemma form, Dan see the turtle. So this the tense of saw has been lemmatized to see. The plural of turtles has been lemmatized to turtle. So this is a part of the process. And the dependency tree example of this, we have our plural noun, the determiner, the turtles. So the dependency of the turtles, the determiner with the noun. And we have an object modification, saw the turtles. And we have a noun subject dependency here where Dan saw. And again, there's a nice online toolkit that we can play with, core-nlp.run. Now I think that, I'll just check that URL. Yeah, so here we can type in an example. Ben is ready for more coffee. This online toolkit is kind of nice. It gives us a few different NLP processes that we can try. So let's try looking at the lemmas of that. It supports multiple languages. So if you do speak another language, try that out. And it's got a pretty interesting loading animation there. So the lemmas for that input sentence has been conformed to that form, that common word be, and the rest of it's pretty straightforward. So let's have a look at the named entities as well. That didn't pick that up. So looks like the named entity module here is probably expecting a capital. So there it's identified me as a person based on the syntax. And have a look at the dependency pass for this input. So we have, again, the noun subject, Ben is ready. So that's our subject in the phrase. More coffee. So if I had just Ben is ready for coffee, we wouldn't have this this modifier, and we have the case. So this shows us the ways that the parts of the input sentence depend on other parts of the input. So that's can be this will be used in more sophisticated techniques where, say, in a conversation, an NLP tool might be trying to identify when somebody is talking about somebody else, and through that conversation use reference such as he said, she said, they said, and then skip over, maybe further in the conversation, I might introduce another named person, and then he said, they said, to know who that person's talking about at that point. We can use these processes of dependency passing to work out who the subjects or the modifiers who's being spoken about at the time. So with all of those bits of the speech or the bits of the text chopped up, tokenized, tagged, labeled, and with the relationships between them all graphed out and marked out, we can begin to try and understand what's happening in the language, what some of the meaning is. A common activity here, sentiment analysis. This is used a lot in, say, product reviews, online shopping, chatbot interactions. So a really sophisticated analysis of a recent Australian election where the tweets around the period of the election were analysed to identify positive or negative responses to the political messaging. So it's a process by which the input text is rated as being a positive or negative, and usually has a score, a value, percentage value. We can demonstrate this at the website Comprehend. Again, I'll put that in the chat. So on this site, we can scroll down a little bit and we can type some text in there. "8 a.m. lectures are too early. Let's analyze that for sentiment, and it's rated that as 74% negative sentiment. Be interesting to try changing that to 8 a.m. lectures is super early. Let's analyze that, see what it thinks. Still rates that as negative, but it's because of this word super. So it's, I think it's interpreted super as being a positive, and so the general phrase 8 a.m. lectures are early is likely to be, let's see what the score of that is. So there's our base, 8 a.m. early. Oh, okay, so that's interesting. So 8 a.m. lectures are early, that's sort of like half negative. If we call it super early, so that's not much different. Excuse my English. 8 a.m. lectures are way early, so there's likely to be using a dependency parser to modify early, and so way early being an adjective is likely to be increasing the rating. So if we try extremely early, 74%. So this little tool can also pick up an emotion rating and can potentially suggest these other sort of understanding, trying to understand the meaning of the term, of the input. Let's try a sentence. I like seeing turtles in the lake. That gives me a happy score. Oh, only not even 50% happy. So yeah, generally positive, makes me happy. So the intent, the intent labeling here looks like it's trying to, so sort of performing like if it was a spam filter or a categorizer on something like an email system. So if an email came into a messaging system that had this, it's likely to end up as spam because it doesn't seem like it's meaningful English communications. So this text analysis is being developed by an organization that must provide services to business. So some of these are just useful to play with. You could potentially build something like these into a system that automatically tried, nice. A system that tried to sort communications into, say, particular parts of an organization to respond to. Lots of different applications for these. So this sort of tech is often behind chatbots. When you go to a website and one of those little things pops up, then as you start typing into those, the chatbots will either respond to it if they have the AI to based on knowledge-based information to help with your issue, or potentially hand it over to a human. If your communications in a chat interface were highly abusive, it's likely that they'll just that they wouldn't hand you over to a human if they thought that it was going to be problematic, or maybe they would hand you to a special resolution department to deal with very upset customers. So these, I'll try this one too. So fully sick. This fully sick is some Australian slang. So developing these kind of systems, we need to be considerate of localization. So if I put in fully sick, the sentiment is emotion, the fear value is very high. Whereas if I was to be using that in my day-to-day conversation with my street machine driving friends, particularly if they happen to come from Victoria, then it would be a term that is more expected to be, my communication intent of fully sick is that it is an expression of great delight. So in this analyzer, it hasn't, there's no localization to an Australian slang context, and so fully sick has been misidentified. So this is something that we need to consider, that if the application is outside of the training domain, then we might be giving the wrong responses. Lucinda's just asked in the chat, to what extent do these tools typically contain a dictionary of words or phrases like this that don't fit within the algorithms? Yeah, so they generally do. So you might train a base system or get a base system, and then there should be some process of adapting it to a local context with either with language models or dictionaries of local context, or by fine-tuning training if you're doing if you had enough data that there was a neural model about it, that you could use transfer learning to a local situation, then you could fine-tune on local data if you had. So it depends on the application. It might be that the system would work fine if it wasn't expecting to pick up or respond to the two terms like that. So fully sick in a chat app on a medical website, you might expect that when someone says fully sick that they are talking about being unwell. But a chat app on a car website, if someone says fully sick, it's more likely that they're talking about a positive thing. So the application of the design is important to consider. And then if you got that mixed up, if you had the car one running on the medical site and someone said fully sick and the response from the car one was, oh, great, good one, love it, show me. That sounds excellent. That's not an appropriate response to someone who's actually unwell.
Okay, so this section, what we're going to look at is a particular tool called Discursus, which looks at how we use language in conversation. So Ben's examples of something like fully sick, if you try and construct that from the individual meanings, clearly it's not going to work. But in a community where people are using those terms, those phrases, they will understand together. So this particular tool started as trying to understand what's happening as we use words in conversation, and how do we actually create some metrics that enable us to track that. Because the hardest thing is to find a particular measure in something as waffly, vague, complex, difficult as a conversation itself. So on this slide, on the left, we have the doctor-patient consultation. So the doctor says, have you been prescribed anything for your asthma? And the patient, David, says, I take Ventolin. The doctor, so how long have you been on Ventolin? So there's some words here, there's some non-words, there's pauses. So along the bottom here, we've got the text transcript. And what this tool is going to do is give us a visual analysis of when the doctor and the patient are talking about the same thing and when they're not. So we need some way of trying to understand that. The simplest thing might be to say when they use exactly the same words, and that would be just word matching. But it's a little bit more nuanced than that, because if you look at the first two, the doctor is talking about prescribing, asthma, David doesn't use the same words, but clearly Ventolin, they're talking about the same thing. So if you have a look at the right, on the right, the red box and the blue box are going to form a diagonal of turns. The size of it is this is not actually scaled to the size of the conversation here, but the size of the box usually says how many words are in that utterance, in that turn. The color tells you the speaker, so the doctor is in red, the patient is in blue. And then beneath that diagonal, red-blue diagonal, is a triangular box, which is half red and half blue. And that shows when they're talking about the same thing. So if they're not talking about, if they're completely different, that box will be completely white. If they're talking about exactly the same thing, it'll be really intense color. Now, this way of looking at similarity is called conceptual recurrence. And a conversation is turn taking. One speaks, the other speaks, one speaks, the other speaks. And the idea of trying to map where they're talking about the same thing comes from communication accommodation theory, or CAT. So all of these, there's a lot more depth in terms of them. We're just going to say there is a theory of communication called CAT, which underlies this. There's a whole technique of how you calculate this kind of recurrence. And very quickly, we're going to go through how we build this into a visualization. So you don't just want when the words match, you want a concept that matches. So how do you create a concept for something like Ventolin? And where Ventolin is used in a text, so this is a technique that looks at a whole set of conversations, doctor-patient conversations, or one reasonably extensive conversation, and looks at when the words occur together. Asthma, subscribed, Ventolin, puff at times, day. There would be a whole lot of other words that have zero correlation with Ventolin. So Ventolin, the word, and Ventolin, the concept, are at two different levels of analysis. The concept is an entire vector. So what Discursus does is it builds a concept model for a whole series of terms. In English, in a conversation, you might be drawing on 5,000 words. You have a vocab of 50,000 words, but there are about 200 or 100 key concepts. So what the system will do is it will build these concept vectors. Okay, so if we look at the right-hand side here, the evidence terms, the evidence terms, there are thousands of them. The concepts, there might be hundreds, there might be 10 themes or so, or even less. Okay, next. So having built the concept model, on the left-hand side here, we can see what we do is tag the utterances. So look for evidence of concepts in each utterance. If there's enough evidence, then code that utterance with that tag. And then the next step beyond that is similarity. So how do you measure whether two utterances are similar? So if the doctor's talking about a series of concepts that all share similar concept vectors with the patient, then the utterance similarity would be quite high. And if we have n utterances, then we've got n squared onto similarity measures. Okay, so can we visualize this? And that's the next slide. So the visualization in this case, we've got the doctor in blue, the patient in red, and we can see the direction, whether the, time starts in the top left corner and goes down to the bottom right. And this diagonal underneath is showing where each utterance is repeating earlier stages of the conversation. So Ben, I'm not sure if this is going to come through, but there's a whole series of animations for this. Did they come through? If you click next, what do we get? Yes. So starting with engagement blocks. So if in a short period of time, there's a lot of intense activity, people are talking about the same thing, then you'll get these small blocks that are densely colored. Okay, next. And the question is, does that give rise to further issues within the conversation? So you can actually look at this vertical column and see that early on in this doctor-patient consultation, the issues that the patient raises right at the beginning keep recurring. If in that column it's red, it says the patient's repeating themselves. If it's purple, it says the doctor is repeating the patient. Okay, next. The interesting thing is sometimes an engagement block is almost white beneath it. And this is something that's very hard to find in conversation, but in this kind of visualization, you can see that that engagement block actually closed off part of the conversation. So this one, the doctor was actually investigating whether the patient's dizziness was caused by alcohol and came to the conclusion that it wasn't. And so there was an intense discussion around that, and then that got closed off. And so this white space is something that you can see in a visualization that's quite hard to see otherwise. Next. Okay, so we had that introductory stripe based around what the patient said. And one of the things in our doctor-patient conversation is quite often you'll get to the end and the doctor will summarize where they've got to in terms of their differential diagnosis with respect to all the different parts of the conversation, the evidence that's coming through. So you get this summary stripe at the bottom. Now, this particular conversation is one that is used to train medical students as a really good conversation. And the visual analysis, it only takes a moment to learn how to read these, but it's quite useful to be able to see the different features of what is a good consultation. Next slide. Now, this is a question for everyone listening, and you can put your answers in the chat. The doctor's in blue, the patient's in red. It's a real doctor-patient conversation, and we've just blown up a small part of that. What is happening in this conversation? It could be questioning, but if you have a look, is the doctor asking different questions? Or is the doctor saying, is the doctor repeating themselves? And so the answers from the patient is very, very short. And what's happening is the doctor is actually ranting in this particular one. It could be lots of yes, no questions, but it's if so, it's the same question over and over and over. It's not a series of questions. If it was a series of questions, you wouldn't see that full blue triangle all the way down to the bottom left corner. So when we showed this to the discourse analyst for the very first time, this is the first time she'd ever seen Discursus, taught her how to view this, looking at real conversations, and she picked this one up and she just said, I know who that doctor is. Very characteristic. Not a bad diagnostician, but after diagnosing whatever it was for the patient, this rant came up pretty much every time. So what can a discursus visualization show? And on the right-hand side, whenever you do a visualization, and this is getting to a computer science issue rather than a language issue, but a visualization overview is the first one. See the whole conversation at a glance. So Discursus is quite good for up to 200 turns in a conversation. The other thing it can do is reveal points of interest at a global level. The second part of a good visualization should enable you to zoom to examine the detail. So you should be able to move, if you've got a visualization tool, zoom in, or if you're doing an active examination using visualization, be able to reveal specific patterns. So like this one, all these different patterns have names. This one's a checkerboard. Number 3, show features of interest and hide other details. So how do you actually zoom in on the things you're interested in and not others? And usually there's a way of filtering. So you might filter for when the doctor and patient are actually talking about asthma. And then the fourth one is tracking metrics through the conversation. So because that lower diagonal is actually a representation of numbers, you can actually plot those numbers on graphs and see an interaction between 2 or more people in a conversation. Okay, so I'm not going to go through this slide in detail, but just to say you can look at those numbers in that lower diagonal and actually specify a whole series of different metrics. We talk about each one of those squares under the diagonal as some kind of recurrence primitive. And these are, if you like, the heartbeat. You measure a heartbeat and then you can plot that over time, and a cardiologist can read a lot into that. Similarly, this recurrence that comes out of communication accommodation theory is the heartbeat of conversations. It doesn't tell you everything about a conversation, but it helps you understand when people are talking about the same thing, talking about different things, when a conversation is moving, when it's stalled, when one person is dominating, when people are ranting, when they're not talking about the same thing, when they're talking past each other. So there's a whole series of different things you can do here. So that's what there's an entire table of these, how you create recurrence metrics for multiple participants. And then out of those, you can create different speaker profiles. And one of the things we showed is conversations between adults and children with autism compared to adults and children without autism, or typically developing children. The children themselves didn't necessarily show much difference in terms of speaker profiles, but the adults did. And it was quite interesting to the researchers who were studying this, because they thought the adults were doing the same thing in every conversation. And they discovered through plotting what the recurrence was, how much work the adult was doing compared to how much work the child was doing. The other thing you can do is you can start with these, a complete conversation. So the pyramid of metrics, which is the one down in the bottom right corner, you can start off with the full conversation, and then you can condense it to a network of person to person if you've got a number of people speaking, group to group. So you could use it to analyze, we've analyzed conversations where experts and lay people are in a room and the experts are all talking to each other, and the lay people get a little bit of a look in, but the experts repeat each other and not the lay people. Or you can look at the amount of recurrence where people are all talking around the same topic versus talking around different topics. The software is actually available for UQ. It was developed at UQ. It's now being maintained by Dan Angus, who's at QUT. So if you would like to have a play with this, you should be able to get a copy of it. If you can't get it through the usual software on site, you can write to me and I can get you a license for it. Ben, are we?
So maybe we should set up have a workshop in using it.
Sure. Yeah. It's pretty easy to learn. Like all of these, it all revolves around data. So having your data coded in a way where you have one speaker per line, and you just use standard encodings. And then from there, it's pretty quick to actually go beyond that. A lot of people try and use it to analyze ordinary text. And there are actually other tools like Lemmatizing, which could analyze a lot of text. This is specifically set up, this one, for analyzing interactions in something like a conversation. So interaction in interviews is a particularly good one, where there's actually a conversational component to it. Okay.
Hey, Janet, if I just go back to the beginning.
Yeah.
In the very early stages of when you're coding the data, is it using NLP techniques like tokenization and lemmatizing, these sort of processes in here?
Yeah, there's a big question around whether you should or shouldn't. The people who like NLP would say, of course, you'd use, of course, you'd lemmatize if you could. The way people use words in practice, talking about something in the past and something in the present. If one person uses the past form and someone uses the present form, it can actually mean something really different. If one uses the plural and the other doesn't, that can also, it can sometimes mean the same thing, but it can sometimes not. And so Andrew Smith, who was the theorist who really put the ideas behind this together when we first started working on it, was adamant that the text should show you the concepts, not drawing on background. So in this particular one, it doesn't, this analysis wouldn't start with just the doctor and the patient with just this much text. You'd actually have about 100 utterances, and it would go through and create the concepts over the entire 100. It's not an incremental system. It's a system where you would analyze after the fact. And so the way we set up Discursus is we followed Andrew's advice. So there's no lemmatization, there's no part of speech tagging. You don't have to go through and say asthma and Ventolin are related. If they're used in a sentence, they will be related. If they're not used in a sentence, it may well be that in this conversation, they're not actually related. So we were looking at this in the early stages where a doctor is using very technical terms and a patient is using non-technical terms. If they use each other's words, then there actually is a common ground they're creating together. If they refuse to use each other's words and there are no utterances where you connect the technical to the non-technical, then as far as that conversation goes, what the analysis would say is those concepts just don't bridge those two worlds. And you're actually better not having a background dictionary that tells you what the technical words mean. Because if the doctor is not using the non-technical words and the patient's not using the technical ones, you haven't connected. So one of the things that conversation is really interesting is where it creates common ground. It's going beyond the generative component of pointing out things in the world, identifying, labeling, naming, instructing, to actually, you can identify people in a group by the choice of words they use, or they can create ironic meaning by belonging to a given group and then using words that might be taboo for others to describe their group. They can use it to describe themselves, but woe betide anyone else who uses those words. So the subtleties of conversation go way beyond the technicalities of what words actually mean from a dictionary point of view.
Thanks. I just looked up, looks like the Discursus website is down. So okay, we might have to follow up. Lucinda, Hunter, if you're interested in playing with it, follow up. We'll work on that, getting access to the program. Okay, so we're getting close to the end. The last couple of NLU techniques, natural language understanding techniques that we'll look at, intent classification and slot filling. So this is a process that a technique that's used a lot in virtual assistants, personal assistants, online booking systems, or speaking into phone. Make an appointment at 3 o'clock tomorrow. How do we turn that spoken instruction into some rules or some an operation or a command that a calendar application can understand and make an appointment with a reminder for? So slot filling is a process of taking out tokens, identifying meaningful tokens in some input and labeling them, similar sort of way that we saw with named entity recognition, but the slots themselves have different types of, or different characteristics. So the example here, show me flights from Brisbane to Melbourne on Saturday, can be passed, and the intent in this instruction is to show me flights, to give me some transport information. The Brisbane term here is can be used to fill the slot origin. Melbourne can be used to fill the slot destination, and Saturday fills the date slot. So this input text can be passed, and what the booking application might need are these slots of, well, what does it need to complete the command? It needs to know the origin of the flight, the destination of the flight, and the date of the flight. If there are other parameters that are required, then these are other slots. So the slots are filled, then the instruction can be passed on to the application. So a travel booking application would have different slots to something like a chatbot or a calendar reminder, or if you speak to a music application, play me some music that I would like, then the intent would be play me some music. That I would like is a very ambiguous statement, and would rely on the history of the person to be able to expand upon what that might mean, and that might take into some other NLP tasks, or similar to what Janet was talking about with the channels and the vectors. So going from a very general term to something specific. Play me some music from the Beatles Get Me Help album, maybe a bit more specific, and we'll be able to fill some slots easier. So slot filling, we'll use this in coming modules when we're developing chatbots. Context-free grammars, this is not so much an understanding thing, but a process that's used in those some of those other techniques. So context-free grammar is a way of defining a language. So remember that languages have grammars. Grammars are sets of rules that describe structure in a language. So natural languages or human languages, the grammars can be incredibly complex, and not all natural languages, well, these context-free grammars tend to be much more structured and more rigorous than the natural language grammars, and context-free grammars define formal languages. So we can use context-free grammars to describe rules for how to pass or to generate natural language, but there is dispute over whether any natural languages can be comprehensively described by context-free grammars. Some people say no, other people say that Sanskrit can be, so this is an ongoing debate. We can use context-free grammars to generate language by following rules of replacement. So we see in the middle column, we have, yeah, English is certainly not context-free language. Even some people will say that Latin possibly is, but the Sanskrit example is really lovely. I'll put a link to that in the Slack channel later. There's some really nice examples where it might be that nobody actually knows how to pronounce Sanskrit. So when it was used, it might have not been, and then as the language has not been used, and we rely more on the documentation of the language to understand it, then maybe the documentation of the language is context-free, but the use of it in day-to-day may not be. So here we'll see the structure of a context-free grammar is that essentially you have a bunch of rules, and the rules give sequences of replacement. So the primary rule here is that we have a starting symbol S, and then it is replaced with a sequence of other tokens or symbols. So I can use these rules to generate a sentence or a sequence by replacing symbols on the right-hand side with other rules that I have in my grammar. So the full grammar for this is a very, this is a toy grammar. It's just made for demonstration. There's a number of rules. We have these D rules, N rules, VP rules, V rules, and ADV rules. So these could be anything. There's the D is here being used for determiners, so grammatical terms at the A, and the N is being used here to denote some nouns. So hey, how about that? VP is a verb phrase. So here we're unpacking whenever we see a VP in our grammar, we know that we replace it with a V and an ADV, and the V is a verb, and here are our adverbs. So we can, by convention, use part of speech type labels, and that helps us to read the grammar, but you could use emojis. So to actually perform this grammar, or to execute a grammar, we start with our S token, and then we go through a series of replacement of the leftmost symbol. So the other terminology here is we have non-terminal symbols and terminal symbols. So when we have so a non-terminal symbol is something that can be replaced by another rule, and a terminal symbol is something that doesn't have another rule replacement. So that's a final state. So our S, we have a rule for S, so that's non-terminal. So our first activity is that we replace the S with the DNVP. So this comes over here. Then we look at our new sequence, and we see that can the leftmost symbol be replaced by another rule. And yes, we see that we have a rule for D, and so we can swap out the D for one of our options. So options are designated by this vertical line, the pipe character. So again, we'll do this, we'll perform that action, we'll replace the D with one of our terminal symbols, A or V. I've chosen A. And then we have our sequences A, and then N and VP. So we perform that again. We have a look to see, do we have any rules for N? And yes, we have a rule that says N can be represented by man, woman, or goat. And so we swap that out. So we go through that process of swapping out the leftmost non-terminal symbol in the sequence, and eventually we end up with an utterance or a sequence of strings that satisfy the rules of the grammar. So this would be a conforming sentence in this language. We can reverse that and use these context-free grammars to pass some text and to see if that text conforms to the grammar of the language as well. And so this is where it can be used in programming languages to validate, or as a compilation process to see whether the syntax of the language is accurate according to the rules. People use these to also generate poetry, which is quite nice. We might even do a bit of that in the prec. But they are often used in these processes of finding, or particularly for generating these instructions. So when a chatbot might use these context-free grammars to generate language that is at least a little bit like English. Something to note there is that the rules can get extremely complex if you're trying to make a language like English perform in a context-free way. I chose terminal symbols that at least gave some sort of semblance to English here, but you could, it can get to be quite gibberish depending on the setup of the grammar. So language generation topics we'll cover in detail in the future module. So there's some really fantastic neural methods for creating language, generating language these days, which are just almost indecipherable, or unable to tell the difference between a human generation of language. So we'll go into detail about that in upcoming modules. And that is all for today's lecture.